this is, of course, the 50th anniversary of our first step on the moon. It's hard for some of us to believe it's been 50 years. How can we all be 39 and it's 50 years? But here is the historic coming down the ladder. Actually, no, this is the second man coming down the ladder because there was no one to take color pictures of the first. We just had those fuzzy black and whites. And so many people are doing films, books, television specials, articles in all the media, all about the astronauts. So I thought as an astronomer, it would be my role to talk a little bit more about the moon itself. Nobody seems to be talking that much about the moon, and I want to acquaint you with some of the most interesting things about our moon. First of all, it's odd that we have a moon. None of our neighbors have one. Mercury doesn't have a moon. Venus doesn't have a moon. Mars doesn't have a... Well, Mars has these 2 captured asteroids that look like diseased potatoes. But in general, those are not considered the kind of moons you'd bring home to mom with pride. So really, none of the inner planets like us have a moon. Why do we have one? And we'll talk more about that. We'll talk about the reason that we in particular have a moon. We also have a relatively large moon. Here are the 2 to scale in terms of size. Our moon is about 1/4 the size of planet Earth. And that's pretty big. None of the planets that do have moons, the outer planets, have a moon anywhere near as big in terms of the comparative size of the 2. There's quite a bit of surface area on the moon. It's a little less than the size of Asia, so there's quite a bit of territory there. The gravity on the moon, as I think many of you know, is less than the Earth, about 1/6. So if you weigh 180 pounds on Earth, you'd weigh only 30 pounds on the moon. That's a lot better than Jenny Craig can do for you, right? So the astronauts, of course, felt this. They really felt unusually light, and they took to leaping around, and NASA had to tell them to cut it out because the nearest doctor was 240,000 miles away. Also, the moon has no air, no water, so it's important to remember to bring your spacesuit. There is day and night on the moon, but each lasts about 14 days. So there are 14 days of sharp sunlight and then 14 days of utter cold darkness. Of course, the Apollo missions went during the daytime. You would not send astronauts during the moon. And that, by the way, is why on the pictures we have of the astronauts, we don't have stars on the pictures because they're taken in daylight, and the kind of exposures you need in daylight don't show the faint stars. This is always a disappointment when there's that explanation for the conspiracy theories and not that it was filmed in a Hollywood studio. So here is a scale model of the Earth and the moon with distance shown. Many people think the moon is a lot closer than it is. You actually have to put, folks, 30 Earths side by side to get to the moon. It's further than most people think. So images like this are misleading, but really beautiful. This is one of those pictures that we now have of the Earth-Moon system taken from far away. This happens to be a spacecraft 31 million miles away, looking back with its telescope on the Earth-Moon system. And you see the moon slowly making its way across the face of the Earth. But it's a lot further away than that seems to imply. Now, another thing that's important to know about the moon is that it goes around the Earth at the same rate that it goes around itself. Now, does that make sense? Let me say it again. The moon goes around the Earth at the same rate that it turns around itself. Now, if you don't know what that means, try it at home. One member of the family stand in the middle, and another member, maybe a junior member, go around this middle person and turn your shoulders at the same rate that you're going around. You'll find that that means you always have one face toward the central person and the other face away. And that's what happens with the moon. There's a side of the moon that always faces the Earth, and there's a side of the moon that always faces away from the Earth. So until we had the space program, we only saw the near side of the moon. The far side of the moon was completely invisible to us. This is called synchronous rotation. By the way, this is something gravity likes to do. Gravity, like your uncle, is cheap. And that means it likes to get into the sort of minimum energy configuration, and that's lower energy when one side is facing toward the Earth and the rotation and the revolution are at the same rate. That's lower energy. So there is a near side and a far side, but with apologies to Pink Floyd, there's no dark side of the moon. The sides of the moon get lit up and get dark in this 14-day cycle, but no part of the moon is always dark. Only after the space age began did we see the other side of the moon. Generally, all we saw was this. This is a really nice picture of the near side of the moon. And what I want you to look at are the dark splotches. That's the technical term, the dark splotches. Now, can you look at those and tell me what shape they are? I want to submit for your consideration that every dark splotch is round. Now you say, no, that's not true. I'm looking at the picture and some of them are really weird shaped, but those weird shapes are actually superpositions of round shapes. If you look carefully, all the shapes are round with some round ones on top of other round ones. And the reason is that every one of those dark areas was made by some large cosmic chunk hitting the moon so fast and so hard it exploded, and these explosions always make round craters. Eventually, lava from within the moon filled in the darker craters, and then other hits came on top of them, were also filled in, and so you get all these superpositions of round craters testifying to the violent youth of the moon. And we'll come back to that a little bit later in the talk. Now, there's more to the motion and the cheapness of the moon. It turns out that because the moon and the Earth are connected via the tides, the moon pulls these regular tides on the Earth where the water rubs against our planet. It turns out that the Earth and the moon can actually exchange energy. And most of us didn't learn about this in school. So if this is a surprise to you, let me be the first to tell you. Because of this exchange of energy between the Earth and the moon is moving further away from the Earth. And to pay for that, the Earth's spin is slowing down. What? Say that again? So the moon is actually getting energy and able to move further away. And somebody has to pay the bill, and the Earth pays the bill, energetically speaking, by slowing down. So actually, the day is getting longer, the Earth is spinning slower, and the moon is moving away. Now, this probably leads you to ask the question that I always told my students was the number one scientific question to ask, which is, why should I believe a word of this, right? What? The moon is moving away? I didn't know that. And the Earth is slowing down? How can that be? So a little later we'll talk more about this, and I'll show you how the Apollo missions really proved that this was true. We already had evidence before, but they made it absolutely clear. But we'll talk more about this after we talk about the Apollo missions. So the moon is the only object in the sky which changes shape regularly. This I think everyone knows. We call this the phases of the moon, and there's a regular monthly cycle of the phases that it goes through. This is because as the moon goes around the Earth, the sun shines on it at different angles, and sometimes the sun illuminates the entire face of the moon. That's the full moon, which we had yesterday, and sometimes the moon just does a little bit of a crescent, or is completely invisible, which we call the new moon. And the full moon has been an object of great fascination for all cultures. Here's one of my favorite pictures of the moon. This is taken with a telescope lens, of course. This was taken by a local amateur astronomer, Rick Baldridge. What you see there is the Lick Observatory on Mount Hamilton, and then the giant moon. But this is sort of a nice introduction to what I want to mention briefly, which is the moon illusion. And I think you've all been subject to the moon illusion. When you see the full moon near the horizon, it looks really big, right? Gigantic. And you see that same full moon just a few hours later at the top of the sky, and it looks much smaller. Now, we've taken photographs, we've measured them, and the moon is exactly the same size. There's no difference. But what's going on is your eye interprets the moon differently when you have something to compare it to. On the horizon, you have buildings, trees, chubby neighbors, things you know that you can compare the moon to, right? And it looks very big when you have a sense of comparison. When it's all alone up in the sky, you don't know anything about its size, and it looks much smaller. So this is an interesting fact about the moon. I wanted to mention now and look at what does the Earth look like from the moon. We've talked about what the moon looks like from Earth. What does the Earth look like from the moon? And this is one of my favorite Apollo pictures. We're looking at an Apollo 17 picture. And remember, the astronauts had to land on the near side because they had to communicate with the Earth. And because they landed on the near side, they could see the Earth. If you had landed on the far side, you would not see the Earth. And this is going to translate into different real estate values in the future, right? It's going to cost more to buy a house on the near side of the moon where you have Earth views, right? And less on the far side where you can't ever see the Earth at all. Anyway, it turns out the phases of the Earth, as seen from the moon, are opposite the phases of the moon as seen from Earth because of the way the sun shines on it. And so you can see the corresponding phases. When we see little of the moon on Earth, moon observers would see a lot of the Earth on the moon. So these are, I'm sure, things that real estate agents will point out in the future. So what did we know about the moon before we visited, and what have we learned since then? I want to show you a fake picture of the moon because it's one of my favorite pictures. This was actually 2 pictures of the moon pasted together. And you see how the shadows are much better than the previous, previous picture I showed you? This is a half moon and another half moon pasted together at the Lick Observatory. And the reason this is good is because then there are shadows, and you can see the shadows are opposite on the right and left side, but all the craters stand out more when you have this kind of shadowing. And so you can see that the moon is covered with craters, not just the big black and dark ones that we talked about, but craters everywhere. And we divide the moon into 2 kinds of terrain, the dark regions, which are called the Maria. Maria, not a character in West Side Story, but it means seas or oceans in Latin. They thought early on that these dark areas were smooth, and therefore they must be oceans on the moon. And many of these Maria are named after emotions. So we landed in the Sea of Tranquility with Apollo 1. And then the other areas, which are lighter and more cratered, are called the highlands because they're higher than the low craters, the low Maria. And generally we know that about 17% of the moon is Maria and 83% is highlands. Now, if you're looking at this picture, you should be shaking your hands. No way, I'm sorry. 17% is Maria? That's not right. Look at how much of this picture is taken up with the dark splotches. So this leads us to the next big discovery, which is the backside of the moon. The far side of the moon has far fewer Maria. And we're not entirely sure why. That's still a mystery. The crust is thicker. We think the Maria formed early on when some part of the moon was still molten. And so when the giant impact craters formed, here's a kind of picture of this. When the giant impact craters formed, not only did they carve out a big bowl, but then from underneath, some lava seeped up and filled with dark lava those giant bowls made by the impact. Later, the moon had cooled enough so that lava inside the moon had congealed and was no longer available to come to the surface. And so the later craters are not filled with this dark material. They have a much lighter appearance. Right. So here is, if you haven't seen it before, the far side of the moon. And you can see many more highlands and far fewer maria. And as I say, we're not sure why that is, except we do know that the crust is thicker on the far side. So we knew a little bit about the moon before we went. And when the space age began, the moon was very much on the minds of our leaders. So here are some of the firsts that happened in terms of moon exploration. You may know some of these and not others. In September 1959, the first spacecraft to reach the moon was the Luna 2 from what was then called the Soviet Union, today Russia, and it just crashed. But they didn't care. They were first on the moon. By October of that same year, the first flyby took place, and the Luna 3 spacecraft was actually able to take photos of the far side of the moon. And they were terrible pictures, but sensational for just existing. We had never seen the backside before. In 1966, the Luna 9, still Soviet mission, was able, I should say, to soft land on the moon. And that was the first robotic soft landing. And then 3 years later, Apollo 11 was the first human to take a step on the moon. But the firsts are not over yet. Although many spacecraft have orbited the moon and shown us the far side in exquisite detail, no soft landing has happened on the backside of the moon. So in January of this year, the Chinese soft landed the Chang'e 4 spacecraft, and it actually had a cute little rover called the Jade Rabbit. I'll show you that. And it was able to tool around on the backside of the moon. But of course, we had the first landing, the first planting of a flag, and of course, the first human geologists, because every astronaut was trained to notice interesting rocks and to pick them up and bring them back to Earth. And we'll talk a little bit more about that. Not only did we land on the moon in 1969, but even better, we came back, which was a very important part of the mission. Right here's that historic photograph of the astronauts rising to meet the command module, and then all of them returning to Earth. When they got back to Earth, they were quarantined, as many of you may remember, because we were worried about the possibility of there being moon germs that in some way would infect us on Earth. Even though the moon has no air and no water, we were not 100% sure that it was safe, and so they spent some time in quarantine and then turned out to be just fine and were released back into everyday life, although they never had an everyday life after that. The further Apollo missions not only sent people to the moon, but cars. Here's what was called the Dune buggy on Apollo 16. By the way, these cars were electric cars. They cost $38 million each. Well, I should say the first one cost $38 million to develop. It was hinged, so they could fold it up and hang it up in the spacecraft, and the top speed was 8 miles per hour. So a Tesla it was not, but it was a very useful electric car for exploring the moon. The other thing that the astronauts did, of course, was to take and set up scientific experiments. There was a primitive suite on Apollo 11, and then much more sophisticated suites of instruments and things that they would leave behind to measure conditions on the moon. Here's a picture of one of them all set up. So let's just make sure everybody knows the history here. How many people walked on the moon? My students were never sure when I was teaching. How many people walked on the moon? 12. 12 people walked on. Of those, how many were scientists? One. Just one. Harrison Schmitt at the very end, the very last person was a scientist because they wanted test pilots for the most part. And the astronauts all brought back rocks for a total of 842 pounds of rocks being brought back. And by the way, those have now been led, not all of them, but those that NASA has let out to scientists, some 15,000 different little pieces and samples have been let out to laboratories around the world. All right. So among the instruments that were left on the moon were seismometers, measuring earthquakes. No, not earthquakes, but moonquakes. And there are moonquakes. Some we made ourselves, dropping some of our equipment on the moon. Some came when chunks of material hit the moon, as they continue to do. And some came naturally from inside the moon. So we actually know from the waves set up by moonquakes what the interior of the moon is like. But perhaps the most exciting experiment left behind by the astronauts were the laser reflectors. Now, do you remember this? Those of you who were not tuned in at the time or not even alive, let me tell you what happened. We brought to the moon and pointed at the Earth reflective mirrors, essentially, a big square mirror. And then an observatory at the University of Texas was equipped with a powerful laser that bounced the laser beam off the moon and caught it back on its way back to the telescope. So we reflected a laser beam from the moon many, many times. And this allowed us to measure the distance to the moon. Now, you know how this works, right? I'm going to do a little math, but it's car math. So even people with math anxiety are usually okay with car math. So you have a car which is driving at 60 miles an hour, and you cover 120 miles. How long did it take you? 2 hours. Or, if you know it took you 2 hours, how many miles will you cover at 60 miles an hour? 120 miles. So in the same way, we knew the speed of light. We knew when we sent the laser. We knew when the laser came back to within a fraction of a second. And that allowed us, ladies and gentlemen, to measure the distance to the moon to within inches. I'm not kidding, to within inches. And we've gotten better than that, fractions of an inch now. And so over and over again, we have measured the distance to the moon precisely. And what we have learned is that the moon is moving away at 1.5 inches per year. Now, that's not that big. That's roughly the rate at which your fingernails grow. Okay? 1.5 inches per year. So in a century, the moon moves away about 4 meters, 4 yards. But over the many centuries, that begins to build up. So this is the proof I was talking about before, that in fact, the moon is moving away from the Earth. And as I said, the Earth must slow down to pay the bills. And we've measured that too, because the Earth is much bigger. That same amount of energy causes us a smaller change. And so the day is increasing by 2,000ths of a second per century. So there's no need to adjust your watch to this issue, right? But 2,000ths of a second per century, that's a lot over the billions of years of Earth and moon history. So we believe when the moon formed, it was much closer to the Earth and that the Earth was spinning much faster. How do we know this? It turns out there are records in the rocks that record the cycle of day and night, particularly the cycle of the high tide and the low tide. And those rocks confirm what the Apollo experiments have told us, that the Earth is slowing down and the moon is moving away. Well, what does that mean in practice? Well, what that means is that we're going to not be able to have these spectaculars. Do you remember this from 2017? In the United States, we enjoyed a total eclipse of the sun. That was the last time I was here at the Commonwealth Club talking about that. And a total eclipse of the sun means the moon, as we see it in the sky, just happens to be the same size as the sun. This is a total coincidence. But because there is the same size in the sky, the moon can cover the sun, and you can just see the faint edge of the eruptions on the surface of the sun showing behind the moon, particularly where there are craters or there are valleys on the moon. This works because the two are the same size. If the moon is moving away, what's going to happen? As the moon moves away, it will look smaller, and it will no longer be able to cover the sun. So I want to congratulate all of you in the audience on your good taste in being born now, when total eclipses are visible. And why are there not eclipses, by the way, every month? You would think as the moon goes around the earth, it should get in front of the sun every month. But here's a quick way of understanding that. The moon's orbit is tilted relative to the motion of the earth around the sun. And because the two are tilted, the moon is typically either above the sun or below the sun in the sky on this tilted orbit. And so most months we don't see an eclipse. But every 6 months or so, where the two circles are in alignment, it's possible to have an eclipse season, either a solar eclipse, eclipse of the sun, or a lunar eclipse, an eclipse of the moon by the Earth's shadow. It's possible every 6 months to have an eclipse. But the eclipses, particularly the sun eclipses, only happen over a very small part of the Earth. So usually it can take 100 or more years before you get another total eclipse of the sun. But I have good news for everybody. We had a total eclipse in the United States in 2017, and we're going to have another one in 2024. That's a very short time distance between the two eclipses. We're very lucky. And here is the path of it. Put April 8th, 2024 on your social schedule now, kids. Those of us who are older, we have to take our vitamins to make sure we're alive then. But the younger people can make plans, and it's going to go from Mexico through the United States at a different angle than the 2017 one, and then up into eastern Canada. So this is something you can be planning for now, the 2024 eclipse. And of course, the moon won't move far enough away in those few years to make any difference. We still have millions of years to enjoy eclipses of the sun. But anyway, that's certainly one consequence. Now, I want to switch to a question that I think many people have, and we've been able to answer because of Apollo, and that's this question: where did the moon come from? Or to put it another way, how come all our neighbor planets don't have a moon and we have a big moon? And before we went to the moon, we had two theories about why this was. They were very simple. Theory number one: the moon came out of the earth. Somehow something launched the moon out of the earth, and it somehow then went into orbit around the earth because we have gravity on earth, and so the moon is a product of our planet. If that's true, then the moon in its chemical makeup and what it's made of should resemble the earth. The other theory was, if the moon was not from the earth, it came from far away. It was part of some other section of our solar system. It ventured too close to the earth, was captured, and went into orbit around the earth. In that case, the moon should be made up of different materials than the earth. And we used to tell this to students as a perfect example of how science works. You have these two competing theories. Now we're going to go to the moon. We're going to get rocks back. We'll analyze what they're made of, and we'll be able to choose between these two simple theories. Well, of course, nature never is as cooperative as we pretend it is. When we actually got the moon rocks, neither theory was right. The moon rocks were similar to the Earth, but not outrageously similar. And the moon rocks were different from the Earth, but not outrageously different. There was just enough difference that neither theory worked. And you could see astronomers specializing in the moon tearing their hair out in 1970 when these ideas became clear. So, what did we learn from analyzing the rocks? And I'm not going to go into a lot of technical detail, but let me tell you three things that we learned that turned out to be the key to solving the puzzle of the moon. First of all, the moon is very dry. It has so little water, so little of materials that evaporate easily, that we think it's unusually different from the Earth. The Earth is, of course, has a lot more water, and the Earth also has a lot of lighter materials which have gone into our atmosphere. And those materials are missing for the most part from the moon. The other thing is that the moon has much less iron than the Earth does. Iron is a heavy material. On Earth, it sank down into the core of the Earth and makes up the center of our planet. And then finally, we found some light rocks on the moon that looked like, forgive the technical term, geological scum. So what we think happened is that the early moon was, at least on the outside, molten. And you know what happens in a liquid? Lighter things rise to the top, heavier things sink to the bottom. And there were rocks found on the moon, much to the excitement of geologists, which could only rise to the top, could only be on the surface, if the moon was molten. So it's deficient in light elements, it's deficient in iron, and it must have been molten at some time. All of that implies that there must have been heat as part of this formation process. And so we think now that there was a much more dramatic and catastrophic beginning to the moon. This was an idea that two pairs of astronomers on either side of the United States had at roughly the same time, and it's called the giant impact hypothesis. What we think happened is that in the early solar system, before any of the planets settled down into their present state, there were a lot more objects, a lot more bodies going around the solar system than we have today. What we think happened is that smaller pieces gathered together into bigger pieces, and there was a time when there were a bunch of mini planets, small, maybe Mars-sized or smaller planets going around the solar system, and not all of them were on stable orbits, so they would hit each other. And we think early on in the history of the solar system, the early Earth, while it was still quite hot, was hit by one of these Mars-sized mini-planets. Some people think it might have just been a glancing blow rather than a direct blow, but there's discussion about that. But when the two objects hit, it completely destroyed the mini-planet and took off quite a bit of the outside of the Earth. We think whatever iron there might have been in the mini-planet was so heavy in this hot, molten situation, it sank to the bottom of the middle of the Earth, so it became part of the core of the Earth. Light materials like water were evaporated from the debris of this collision, and then the debris itself went into orbit around the Earth. All that was left were the chunks, the violent chunks of this collision, and they went into orbit in a kind of cloud around the Earth, and that eventually coalesced into the moon. And because everything was so hot, all the light elements were lost. Because the whole process was so violent, when the moon formed, it was molten, and so the geological scum could rise to the top. And so this explains everything we've learned about the moon from Apollo and other missions. Was there really such a giant collision? We can't prove that. At the time, the Earth became molten enough, so there's no crater left from that. It all reformed into a sphere. But this is what we now think about the moon. And the moon cooled, then it got hit by chunk after chunk, making the Maria and later the smaller craters. It still gets hit all the time, so its surface is actually pulverized. There have been so many hits that there's a fine dust made up of tiny fragments of all the impacts over billions of years, and it was that fine dust into which the astronauts now stepped and made those lasting footprints on the surface of the moon. Well, let me finish by just saying a word or two about more recent exploration. As you've heard, the Chinese have landed on the moon. This is the lander and the Jade Rabbit rover photographed by each other. And since January, they've been operating on the moon. You've probably read that the Indian mission to the moon, the mission from India, was just postponed. The Israeli mission to the moon failed. There are many countries that have been doing and plan to do moon missions. Pictures of the moon have been returned with incredible precision by European, Japanese, Indian, and US orbiters and landers like this one from China. And what these orbiters have found is the hint that there is water on the moon, which I just explained to you can't happen, right? So what's going on? Here is a diagram showing the poles of the moon, and the blue areas show you where from orbit hints, including vapors coming up, have given us a hint that there might be water on the moon. Now, we've just discussed that water can't be original, right? It can't be left over from the hot formation of the moon, so it must be water that was sent to the moon by special delivery, right? It had to come to the moon later, and what we think happened is that some of the chunks that hit the moon are made of water ice. They're called comets in everyday language, and these comets hit the moon. When they hit any part of the moon, they just evaporate from the impact, and that's it. But if they hit near the poles, where the sun is low on the horizon and the walls of a crater may keep the sun from shining deep into the crater, if a comet were to land in one of these deep craters near the poles, the water, the ice, could reform into ice after the impact and survive there in these deep craters. Now, if this is true, if we went to those craters, we could liberate the icy water. And that's just what we did in 2009. The Lunar Reconnaissance Orbiter sent a part of itself in toward the south pole of the moon. The spacecraft had two parts, the crashing part and the later crashing part. And the first crashing part just made a giant impact. A plume of material came out. The sensors on the second part then looked at that plume and identified a great deal of water in the plume. Here's the picture. It was called the Lunar Reconnaissance Orbiter, LRO, and this was called L-Cross, the part that crashed. And out came the water, which we could measure. So we now know that there is ice mixed with quite a bit of dirt, so you'd have to really refine it, on the backside of the moon. Finally, what about the future? We know that about 25 missions are planned to go to the moon, most of them robotic missions. We ourselves are thinking about a possibility of eventually having, I think I skipped a slide there. Yeah, we ourselves are thinking eventually of having a person mission to the moon. We're actually thinking about sending a woman with the Artemis mission, but it's way behind schedule and way over cost. And what the head of NASA asked for is only a down payment. So whether we'll make it by 2024, nobody knows. But in the longer run, people are thinking about setting up settlements on the moon. Perhaps even on the backside of the moon, where we might set up telescopes and radio antennas which are completely shielded from the Earth by the moon itself. That could be the darkest, quietest observatory we have ever built on the backside of the moon. What a place, for example, to do SETI, the search for extraterrestrial intelligence, where we could listen in for messages from alien civilizations with no disturbance from communications from Earth. Of course, we'd have to have a satellite like the Chinese do, so that as it goes around, it will allow the backside to communicate with the Earth. So these plans are underway, and some people who like to think long range are talking now about whether or not we need a settlement on the moon, because genetically speaking, we on Earth have all our eggs in one basket, if you'll pardon the expression, right? All of human life, all of Earth life is on this planet. If some giant chunk from space or our own neglect destroys the Earth, we're gone. And so wouldn't it make sense to have a separate settlement? Now, whether that should be on the moon or Mars is a topic for future generations to think about. But certainly one reason to go to the moon is because the Earth is a fragile planet which we're not taking great care of. So let me end with the following thought. The steps that we took on the moon 50 years ago, they will be there for millions of years. There's no water, no weather, nothing that will destroy these. Maybe an impact occasionally, but those footprints are pretty safe on the moon. They will be there for millions of years. Can we say the same about the creatures who made the footsteps? Will we still be around then? For now, I think that despite all the problems and confusion on Earth, it's really nice for us to know that we can still continue to ask the big questions like we've been asking about where we come from, and to think of big plans for where we might be going. Because it's those big thoughts, after all, that are the hallmark and pride of being human. Thank you very much. All right, I'm supposed to sit here.
That was
Good.
fascinating and wonderful. Thank you so much. Let me reintroduce Andrew Fracknoy for those who are late to tonight's program. He's Chair Emeritus of the Astronomy Program at Foothill College and former Executive Director of the Astronomical Society of the Pacific. So it's time for our question and answer period. And we've got some great questions here. Thank you for those who've already contributed. And if you have new questions, feel free to pass them on up. What a great jumping off point that you wrapped up with the 25 missions that are planned. And that actually was the core of several of the questions. What would we hope to accomplish with these missions? What sort of work do you see being done there?
So we have to separate the missions into those that are political and those that are scientific, right? Our aim to take people back to the moon is as much political as it is scientific. And again, I as a scientist and someone who, like gravity, is kind of cheap, I prefer robotic missions to human missions. On the other hand, as a science fiction fan, I love the idea of human steps on other worlds. And so the question is the next human mission to the moon just a step toward going to Mars, which I'm really in favor of, that eventually, maybe not in my lifetime, but eventually humans should be on other planets as well. So there are those missions, and then there are those missions which are purely scientific. For example, getting to know more about the backside of the moon, understanding more about its geology. Why is it that there are fewer Maria on the backside? How did the backside get to be less thick in its crust than the front side? There's also a lot we don't know about the origin of the moon. I told you this lovely story about the giant impact, but we really don't know if that was true. And even if it was, how exactly did that impact transform into this system of the Earth and the moon, which are able to exchange energy? And the details of that, there's a great deal to be worked out, and there's a great deal that we're still arguing about at meetings.
Are there things we could learn about Earth from Moon, do you suppose?
Well, I think the main thing we learn about the Earth has to do with big history, if I can use that term. So here on Earth, much of the evidence of the long-term history of the Earth is erased. It's erased by the fact that we have plate tectonics, that the different parts of the Earth are moving. There are earthquakes, mountains are built up, and there are other forces. Water washes over the surface of the Earth, weather happens, teenage children, all kinds of destructive forces happen to the surface of the Earth. And so we are no longer able to read the historical record beyond a certain point. What happened here? Whereas the moon settled down very early to be a boring place, and whatever hit the moon, whatever happened to the moon, is preserved over billions of years. By studying the cratering on the moon, all those holes on the moon, they happened to the Earth too. They just got erased since then. And by studying, therefore, the history of the moon, we can learn more about not just the history of the Earth, but the history of the whole solar system. How violent was the beginning? When did things settle down? How big were impactors over the billions of years?
We have a related question here, and it's a good one, and that is there anything to be gained by exploiting the moon? Are there minerals or things of potential economic value? And if so, how do we get them back? Describe the logistics of.
Great question.
Yeah.
So getting things back from the moon is expensive, right? Even if you got gold in the moon rocks, which there isn't, if you got a lot of gold back, still you'd have to launch it from the moon, get it up into orbit, then launch it back to the Earth, have it safely land in the ocean or somewhere on Earth, and then you could exploit it. So there are very few things worth that. Much more likely, whatever's on the moon can be exploited for whoever's on the moon. So if we actually do set up people, even if only temporarily, they will need water. They will need oxygen. And there are big blocks of ice on the moon, so that which can be used to get water and oxygen. There'd have to be a lot of processes to make sure it's clean water, but we could do that. So much more likely we will begin by exploiting the moon for moon residents rather than Earth residents.
And are there construction materials there? Or how do we go about building human habitation?
Right, so I'm not an engineer, so I'm not going to be very good at answering the details of this, but I will just say that yes, it's certainly possible with the right machinery and with the right chemistry that we can use some of the materials of the crust of the moon to make things. The big problem on the moon, which I should have said more about perhaps, is the dust. The fragments of these billions of years of impact are like fine powder. We actually worried before the astronauts landed on the moon, and in fact before that, before the robots landed on the moon, is there so much fine powder on the moon that stuff would sink in? And you'd have Neil Armstrong take that first step and be a quicksand. He'd be right. That would be very embarrassing on television, right? So they wanted to make sure that the dust was not so deep. And it's not so deep, but it's plenty deep enough to get into everything. When the astronauts went back into the capsule, it was a pain in the telescope to get that dust off their clothes, off the samples, off the furniture, etc. Very, very hard to deal with. And any future moon mission is going to first and foremost have to deal with airlocks of the kind where you could get rid of the dust and not bring it in to the main living area. The problem is that dust is a little bit sharp. It's not fine. It's not been weathered by water, so it has sharp angles and protrusions, and it's not good to breathe in. It gets into your breathing passages, and then they actually complained of essentially the equivalent of asthma from the dust. So we'd have to be very careful about dealing with the dust on the moon.
Thank you. So that poses a real challenge for manned exploration. Talk about the pros and cons, if you could, about robotic versus manned. I mean, clearly that's one of the issues. But
so we've talked a little about this.
Yeah.
It's so much cheaper to do this, right? I mean, it costs dozens of billions of dollars in those dollars, hundreds of billions in modern dollars, to put on the Apollo program. The Lunar Reconnaissance Orbiter cost $500 million, including everything. So that's still a lot of money compared to your home budget, but in terms of the U.S. budget, that was a minuscule part. Do we really want to make the kind of investment, and it will take a serious investment beyond that which the current administration is telling you? It's going to take a big investment to get people safely to the moon, to have their sort of three-part journey that they have in mind for the Artemis project to work. And so the biggest difference is the cost. It's the safety. If a robot probe fails, it's terrible, but it's not the kind of thing that will make news for weeks. It's just a robot that's failed. So it's much more safe politically and in terms of economies to send another robot if one fails. And then in terms of what the robots can do, the robots are getting smarter and smarter. We have robots on Mars that have a laser that vaporizes the rock, smells it, if I can use that term, and tells you what it's made of. That's a smart robot, right? If you can actually smell the chemical makeup of the rocks, that's great stuff, right? And we could do that. We could do that on the moon. We have the machinery to do that. So in order to analyze the rocks, even to drill into the surface of the moon, we don't necessarily need people. Where people excel and where we didn't do enough is having trained geologists select the rocks we're going to bring back. That training, which the astronauts were given some training, they actually studied with geologists, they studied with astronomers at the University of Arizona so they could steer by the stars, by the way. So we astronomers like to brag about our role in the mission. But what we could train the astronauts to do was nothing compared to what a trained geologist could do. And only one geologist went to the moon, and only in the last human mission. So we'd love to send, if we're sending people, we hope we'll send trained geologists next time.
So what might we hope to learn from the rocks then that we have not learned?
So we should get the biggest question we're unsure about, and this gets a little technical, so I'm not going to say a lot about it. We don't know whether we got an unbiased sample of the moon in the way we got the moon rocks, right? Because we were always landing in safe areas. If you've seen the movie about Apollo 11, how Neil Armstrong steered until he saw a place that was really boring, and that's where he wanted to land. All the mission controllers wanted boring. All the scientists were hoping for weird, right? So they landed in the Maria for the most part. They landed in safe places. Now, we know that these giant impacts throw rocks here and there. So when they picked up rocks, we know that they've picked up rocks that were actually thrown into the craters from other crater-making explosions. So we didn't just get the local rocks, we got some from further away. But we're so unsure still of how complete our sample is from these 800 or so pounds of rocks that we picked up. We'd like to land in other places and get a much larger variety of the material, not just rocks, but soil and other material that makes up the moon. And then we'd like to dig. Just like on Mars we're hoping to dig, we'd like to dig into the moon. The moon, we don't think that there's any incredible surprises. On Mars, it's possible that we could find fossilized life if we dig deep enough into Mars. Mars actually was like the Earth early in its history. It resembled our planet. It had lakes and rivers, and life may well have started on Mars billions of years ago. Mars, because it was smaller, lost its air, so then life was no longer possible in the very thin air and no liquid anymore environment of the current Mars. That didn't happen on the moon. Still, digging into the moon might tell us more about the history of the moon, and that would be really good.
Interesting. You had mentioned challenges in hitting that 2024 deadline to get back to the moon. Is that a funding issue or a technology, engineering issue?
Yes.
What's the rate limiting factor there?
It's both. Everything's a funding issue, of course. If you throw enough money at things, they work better. But what we now, again, I'm not an engineer, but what we understand about the Artemis program is that kind of nothing is ready. What they envision is that there will be a giant rocket bigger than the Saturn V rockets, which is now being designed and built by Boeing, and it will be the launch system. And it will launch, before it launches people, it will launch pieces of a moon station, an orbiting moon station around the moon, which will hook up robotically. And then when the astronauts get there, they'll have a kind of home, a mini version of the International Space Station orbiting the moon. And then there'll be part of that a moon lander. So we will come from Earth with this giant rocket. The piece that's left over will dock with this station, and then the station will send its lander to the moon. None of that is ready. They also want a much better spacesuit, which isn't ready. And there are all kinds of cost overruns and technical problems with the various pieces of this, all of which are solvable, we think, but whether they'll be solvable on the accelerated schedule with the budget that the current administration has asked for, that's an astronomical question, a big one.
Is our moon funding cutting into our Mars funding? Are they separate budgets, or could success on the moon accelerate what we're doing with Mars?
Again,
what we learn that
these are political questions, and
Okay.
I don't know.
Okay.
Nobody knows.
Huh.
What we've heard is that the administrator of NASA has asked for a supplemental budget appropriation to go for specifically speeding up the moon human landing program. There's no guarantee that the Congress, in its infinite wisdom, will fund that extra money for NASA. There's always a concern at NASA that the human program cuts into the scientific exploration. I don't want to get political, but science is not always the favorite part of this administration's view of the world. There are parts of NASA's budget that have been severely cut, including all projects that look back down at the Earth and might reveal global warming or other politically inconvenient issues. So nobody knows quite how the budget will work out until you actually see the budget happening. But there is always the concern that the more you fund the big human missions, the less they'll be available for the robot missions. And
Interesting.
again, these are political decisions.
And I know they want geologists to go, but what about the rest of us? If anyone who's interested in going to the moon, will there be citizens that are invited?
Well, so I don't know about the moon yet, because although the private programs do have this ultimate aim of putting humans on the moon, they first have to put humans in space. They have to put humans in orbit. And of course, it's a complicated issue. Many different commercial launch companies are hoping to be the first to do X, whatever X is. Get a human up and down. Put a human up there in their own orbit. Essentially, we're repeating the history of the space program with these private companies. Some want to send robots to the moon. They want to have their corporate logo on the moon before another corporate logo. Whether that's an important mission or not, I'll leave to you guys to think about. But so each of these is a big step, and it's not a government project. So I don't want to think about bad outcomes, but the first commercial rocket in which a human being is killed is going to lead to an incredible uproar about whether we should allow this and was it a good idea. Right now it all sounds great. Yeah, let Jeff Bezos go to the moon, yay, etc. But all it takes is one human death or one human stranded where that human chokes to death because the supply of oxygen runs out. And there's going to be an enormous reevaluation. So how much of this should be private? How much should the government step in to guarantee safety, or should they not do it? Because then they'll be blamed. Again, these are way beyond the pay scale of a poor astronomer, but these are all questions we're going to have to grapple with as we get into the commercial space era.
So, quick pivot here. There are many legends associated with the full moon, and even today you hear people talk about bad moon rising. We actually have a question from a member of the audience here asking about the monthly menstrual cycle of women. Is there research or studies into any of this?
Well, thank you.
Yeah.
This is one of my favorite topics, but we don't have time to talk about all the details. You know that the moon is an enormous part of human legend, particularly the full moon. I don't need to tell you guys about vampires and the Harry Potter series and werewolves and Professor Lupin. And even in the human language, right, crazy behavior is associated with the full moon. What's another word for craziness in English? Lunacy, right? Luna means moon. There's a strong kind of human memory association of the full moon with bad things. And even in today's culture, you read about this. Sort of pseudoscience literature says that there are more births during a full moon than any other phase of the moon. People, midwives and others swear to this. judges and others tell you that there's more referrals for crazy behavior, there's more serious crime during a full moon than during any other phase of the moon. And people actually think about this. Books have been written about this, the lunar effect, the lunacy, this, etc. So this was all legend, but now, today, with computers, we can actually do experiments about this, right? This is something we can test. We have a record of when all babies in the United States were born. Why do we have to have the exact date and time of every birth? For the birth certificate. Thank you very much. So we have that, and counties record the birth information. They're computerized. So we can go to any county, take the birth information, superpose on that the phases of the moon, and ask, were there more births in this county during a full moon than other phases? And the answer is absolutely not. We have emergency room admissions because all the health plans require you to put the date and time when people were admitted to emergency rooms. Are there more crazy behaviors, more admissions for gunshot wounds during the full moon than any other phase of the moon? The records say absolutely not. So why is there this folk legend associating the full moon? We think it's because the full moon is really noticeable. You don't think that much about the moon when it's a slender crescent or it's visible during the daytime. You go about your business. But when the moon is full, it knocks your socks off, right? You notice it. You talk to your friends about it. And if something happens during that full moon, a baby's born, a crime is committed, you're much more likely to note that and associate it with the moon. It's really a psychology issue, not an astronomy issue. As far as we know, the moon causes no bad effects on human behavior. So I'm sorry for the Harry Potter fans, but I don't think Professor Lupin is real.
Very briefly, a question about why the moon and the Earth as well is more or less spherical.
Great. Why are the planets in general spherical, whereas the smaller bodies are not? And it goes right back to what I said before about gravity being cheap. The cheapest shape for gravity is round. Think about it. Gravity is measured from the center of an object to the outside of an object, to the surface. If you have an equal and well-distributed world, everything should be equally distant from the center of gravity. What's that shape where every point on the surface is exactly the same distance from the center? A sphere. So when things melt, like planets do at the beginning, or when things are not solid to begin with, like stars, which are all gas, they will form naturally into the cheapest shape, which is round. When things break apart later from a solid state, or when they form in very small quantities so they can't melt, then they're like the asteroids. They look like diseased potatoes. They have weird shapes. But all big things, which were either liquid or solid, turn into round things because of the cheapness of gravity.
Okay. So we've got just a few minutes left, and reaching the part of our program where there's time for just one last question. I think a lot of us are saddened by the prospect of the moon moving further and further away from us. And then, of course, there's a question, what's that mean for us? What's it mean for our tides? What's it mean for the moon? Where's this all headed?
Well, first of all, I'm sorry to introduce this negative thing into your life.
Yeah.
I want to emphasize again that this is a very long-range process. It will take literally millions and billions of years for the effect to become noticeable or significant. And even in terms of how large the tides are, we're pretty well guaranteed good surf for some time to come for the surfers here in California. In the long run, though, the question that we wish we could answer is what will happen first? The moon and the Earth reaching a stable state, which some people predict might mean that the day and the month are the same length. So the Earth slows down enough so that the Earth turns at the same rate that the moon goes around us, which means that there's one side of the Earth that will see the moon and another side that won't, again, changing property values completely. This, by the way, happens to Pluto. Pluto has a giant moon called Charon. and Pluto and Charon have reached this kind of equilibrium where one side of Charon sees Pluto and one side of Pluto sees Charon, but not the other sides. So that whether that will come first or the death of our sun, where the sun will expand and vaporize the inner planets, after which we won't worry about the Earth and its relationship with the moon.
Thank you so much. Our thanks to Andrew Fracknoy. Just a lovely, lovely talk. Chair Emeritus of the Astronomy Department at Foothill College, former Executive Director of the Astronomical Society of the Pacific. Also, thank you to our audiences here and for the great questions and on radio, television, and the internet. My name is Lisa Krieger, science writer for the Mercury News, and now this program of the Commonwealth Club, the place where you're in the know, is adjourned. Thank you.